Modern autonomous AI agents possess immense analytical capacity. They synthesize decades of dense academic literature in seconds and generate flawless code without human intervention. Yet, if you ask that same system to draw a simple methodology diagram explaining its own research logic, the process collapses. While language models have scaled exponentially, the translation of complex, abstract methodologies into precise visual space remains a stubborn bottleneck in automated scientific discovery. An autonomous AI scientist remains incomplete if it cannot map its findings into a clear visual format for human peer review. The system must be able to illustrate its work. Standard end-to-end diffusion models approach a technical diagram as a grid of pixels. When prompted with a methodology, they output overlapping boxes, nonsensical arrows, and text that resembles a dead alien language. This failure occurs because diffusion models attempt to solve semantic logic and pixel rendering simultaneously. They guess at the layout while trying to paint the image. To bypass this, researchers often force the AI to write rendering code, utilizing programmatic frameworks like TIX or SVG. Writing code locks in the structural logic, but the output is entirely rigid. It fails to produce the complex custom icons or the modern aesthetic polish required by top-tier academic journals. The solution requires a structural division of labor. A new architecture, known as reasoned rendering, completely separates the logical layout planning from the aesthetic rendering phase. By defining the layout as a distinct computational step, the architecture targets the core cause of spatial errors. This separation allows the model to finalize the mathematical topology of the diagram before the pixel generator is even activated. Reasoned rendering begins with semantic extraction. Thousands of words of wrong methodology text are fed into a planner agent, which identifies the core entities and maps their relationships. The planner does not draw a single pixel. Instead, it translates those relationships into a purely symbolic layout, a coordinate map, and attaches a JSON file dictating the visual style. Next, a vision language model is deployed as an adversarial judge, known as the critic agent. It evaluates the wireframe for spatial overlaps or missing logical connections, and immediately fires an error signal back to the planner. The visualizer and critic iterate. They shuffle bounding boxes, adjust alignments, and balance the visual weight of the information flow. This computational loop executes continuously until it reaches mathematical convergence. Only then does the image rendering begin. Quarantining the layout phase ensures the structural topology is defined early. This architectural constraint aims to reduce the logical disconnects that often compromise AI-generated imagery. Generating the pixels from that layout still introduces a critical error. The text inside the rendered boxes is frequently blurred or hallucinated. To correct this, the architecture relies on a specialized erase and correct strategy. The system runs optical character recognition over the initial draft, pinpointing the exact coordinates of every corrupted string of text. It then intentionally deletes those pixels, wiping the nodes completely clean. Finally, the system cross-references the original layout JSON and injects crisp, mathematically perfect vector fonts back into the exact same locations. If an illustration contains a single misspelled variable, it cannot be published. This targeted correction ensures the typography matches the rigor of the underlying research. Even with perfect typography, a flat raster image is essentially a matrix of static pixels. A researcher cannot adjust an error or change a color without regenerating the entire file. The AutoFigure-Edit pipeline was engineered to solve this by converting these static raster drafts into modular, editable vector graphics. It utilizes the SAM3 segmentation model to scan the draft image and identify the boundaries of every distinct icon and shape. When the model detects multiple overlapping masks for a single object, it applies intersection over union thresholds. It mathematically merges these overlaps into one cohesive bounding box. A dedicated background removal model then isolates each asset, dissolving the surrounding pixels so only the core object remains. These transparent assets are then mapped directly into an SVG coordinate system. The final output is an editable SVG. Within a browser-based editor, scientists can reposition individual icons or change labels without restarting the generation process. To measure the exact efficacy of this architecture, researchers build FigureBench, a large-scale dataset pairing thousands of long-form scientific texts with their corresponding illustrations. This chart displays the win rates of reasoned rendering against existing baselines across scientific literature formats. Performance on textbook and survey diagrams approaches near perfect accuracy, relying on standardized visual hierarchies that the planner agent easily maps. For primary research papers, the success rate drops to 53%. Extracting entirely novel methodologies and inventing original visual structures to explain them remains a difficult task for current language models. Despite this drop, the decoupled architecture still outscores every existing baseline in semantic faithfulness, conciseness, and aesthetic design across all categories. When put to a blind test with human experts, over 66% of peer reviewers confirmed that the raw, unedited outputs met the rigorous standards required for academic publication. Because the final files are modular SVGs, researchers can fluidly manipulate and adapt the layouts, tweaking the design to perfectly match their hypothesis. This system bypasses the days of labor typically required to manually draft and revise technical illustrations. By enabling an AI to successfully explain its own logic through editable vector graphics, we resolve a major bottleneck in the research pipeline. The autonomous scientist can finally show its work.